let me start this discussion by considering the simplest possible, linear time invariant circuit, right? So let's say you have an RC low pass filter like this, and you excite it with a complex exponential, which is basically saying I take a sine wave, plop it into the low pass filter, and let's say the resistance that we have is fixed with time. It's not changing with time. Okay. Then what comment can we make about the output? How will the output look like? Hello, is my audio okay, or did everybody lose audio?
You're fine, Shanthi.
Okay. All right. So basically, if there was an RC low pass filter, and you put in a complex exponential, of course the output, the strength of the output depends on RC and omega. But what comment can you make about the shape of the output itself? It is a sinusoid, and it basically is e to the j omega t divided by some 1 plus say j omega RC, and so this is h of j omega e to the j omega t, where h of j omega is depends on RC, depends on RNC, right? So in other words, the input sinusoid experiences a gain, right, h of j omega, right, which of course depends on the input frequency. That's all right, but the gain is a complex number. So in other words, it means that it's got it's got both a magnitude change and phase shift. So this is basically like an input sinusoid into a linear time invariant system leads to an output sinusoid. And what comment can you make about the gain of, I mean, in other words, is the gain changing with time, or is the gain fixed with time? Yeah, the gain is not changing. So, and that makes sense because the system is not changing with time. And what basically, what can we say about this gain? Remember that the output is basically h of j omega times e to the j omega t, and therefore h of j omega can be interpreted as the response to the sinusoid divided by the input itself, right? Okay, so this is the response to the sinusoid divided by the input itself. So basically, you can interpret this h of j omega. Again, I'm going to reiterate, even though it may sound redundant. H of j omega is the gain experienced by a sinusoid at frequency omega. And because the system is time invariant, the system's properties are not changing. It follows that the gain experienced by the sine wave is also not changing. All right. Now, let me take another example. Now, let's say, there was a monkey sitting here and was changing the value of this resistance. So the value of the resistance was, some R1 at, for a long time. And suddenly the monkey changed it, reduced the value of the resistance to some smaller value R2 and brought it back to R1. Okay. So intuitively, what would you expect the output here to be? Yeah, well, so, for a long time, the resistance was R1. So you would have some sine wave like this. Then as soon as you kind of, as the monkey reduces the value of the resistance, what comment can you make, or should you expect at the output? Yeah. So basically, you should expect that the sine wave in general attempts to get bigger. Then again, when you increase the resistance, it probably comes back down like this and remains. The envelope again eventually settles to the same value that we had here, right? So in other words, if you look at the ratio of the output to the input, right? So what, in other words, loosely speaking, therefore, what comment can you make about the gain experienced by the sine wave as a function of time? Is that constant or is it varying? Yeah, the gain experienced by the sine wave is varying, and that makes. And why does it make intuitive sense? Yeah, well, because the system is changing with time, and therefore it seems reasonable that because the system is changing with time, the gain of the system also changes with time, and therefore the gain experienced by a sine wave, of course, not only now depends on the frequency like it did earlier, right, but also depends on time. Okay, now so the gain is time variant and is denoted by h of j omega comma t, right? The first argument is telling you what frequency you're putting in. T is, of course, the time. And, if you actually, I just plotted an example output. So the gain was, was fixed, and then is evidently changing, and then again comes back to some fixed value. And remember that, is this number real or complex? Yeah, it is complex. So what that means is that not only is the amplitude changing, the phase, between the input and output is also changing with time, right? If you want to think about it that. Why is it changing slowly? That of course depends on the actual values of the R and the C. This is just illustrative. Of course, if the RC time constant and this R1 and R2 were changed, the rate at which this envelope would change would also differ. All right. The next thing I'm going to do is basically now keep varying the resistance periodically, right? And therefore, what comment can you make about the output now? Yeah, well, it seems reasonable that if you keep varying the resistance periodically, then you should expect to see the output also, the gain experienced by the sine wave should also be changing periodically, right? And so this h of j omega comma t is the gain experienced by sine wave at frequency omega as a function of time. And because the system's properties are varying periodically, it makes sense that the gain of the system also varies periodically. Does it make sense? So now, let's so now we have two periodic things to be worried about. One, of course, is the input signal, which is a sine wave, with frequency omega, and one, of course, is the rate at which you're varying the system, and we're going to call that omega sub s. Let me use a different color. Yeah, that's omega sub s. Okay. Now, if the gain of a system I mean, if the gain is varying periodically with this frequency, right? And 2 pi by Ts is omega s, right? Ts is the time period with which the system is varying, right? So this is basically Ts. So h of j omega t is the same as h of j omega t plus Ts. Okay. All right. So this is a complex, I mean, h. Remember again that h of j omega comma t is a complex quantity. All that we are saying is that because the system is varying periodically with a period t sub s, which is where 2 pi by t sub s is the same as the frequency in radians per second, it follows that the gain is varying periodically with time. Now, if you have a waveform which is periodic with time, you can always express it as a Fourier series, and that's precisely what we do. So this is a periodic waveform, and it can therefore be expanded in a Fourier series, right? What will be the fundamental frequency of the Fourier series? It will be omega s. And why is it omega s? Yeah, well, that's the period with which this waveform is changing, right? And therefore, the fundamental frequency of the Fourier expansion is basically omega s. And therefore, you can write this as, what do you call some Fourier series coefficients times e to the j k omega s times t. It's the sum of the fundamental and its harmonics. The fundamental is basically at omega s, and therefore all its harmonics will be at integer multiples of omega s. And these, I mean, what comment can we make about these coefficients? So this is basically, this is the sum e to the j k omega s times t, right? What comment can you make about these coefficients? They of course don't depend. Very good. They don't depend on t, but what do they depend on? They're complex. That's very good. What else? They depend on the frequency, right? Because so therefore the kth Fourier series coefficient is denoted by h sub k. It only depends on the input frequency and does not depend on time. That's the key. Takeaway, right? So basically, the periodically changing gain that's experienced by the input sinusoid at a frequency omega basically can be expanded in a Fourier series. This is the fundamental frequency, and these are the Fourier series coefficients. And Fourier series coefficients do not depend on time, obviously, but they only depend on the input frequency omega. Very good. I hope this is clear. I mean, as you can see, the notation is starting to get a little messy, right? And it's kind of difficult to keep track of this omega and that omega and this h and that h and so on. So it's I always like to draw a picture and basically derive these myself from scratch. How does the spectrum look? We'll take a look at that a little bit down the road. So the bottom line, therefore, is that the fundamental frequency is this omega s, and omega s is related to the time period by by the familiar relationship. Omega s is 2 pi over Ts. Now the key aspect is that the Fourier series coefficients only depend on omega, and so Now let's put all this together. So the input is e to the j omega t. This is the input sinusoid. The output, the 4, is basically the gain multiplied by the input. The gain, of course, is periodically varying gain. All right. Now, since the gain is varying periodically, the gain can be expressed as a Fourier series of the gain. So, therefore, the output is this guy here multiplied by e to the j omega t, and therefore is you can just take this omega into this guy there, and therefore the output is h sub k of j omega. This is the kth. This is the Fourier series coefficient corresponding to the kth harmonic. Kth harmonic of omega sub s. Is there any limit to omega with respect to omega s? Nothing. There's no limit. I mean, this is this is true for any arbitrary, as long as the system is periodically linear. There is there's basically no constraint. Omega and omega s can be. I mean, omega s is what the system is varying at. You have no control over it, but omega can be arbitrary. All right. So so therefore the output. So now, therefore, what comment can you make about the frequency content of the output? What all tones, if you look at, for instance, if I go and plug the output the spectrum analyzer, what all tones should you expect to see? What all frequencies should you expect to see? Yeah, you should expect to see omega. You should expect to see omega plus omega s, omega plus 2 omega s, omega minus omega s, omega minus 2 omega omega s, and blah 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 blah. So you will see all frequencies of the form omega plus k omega s, where k is an integer. Does that make sense? Okay. How does this differ from a linear time invariant system? Yeah, very good. So in a time invariant system, you only see if the input frequency is omega, the output only the output frequency is omega. The output frequency, you only see one tone at omega. But in a linear time invariant periodically time varying system, you will not only see omega, but you will see a whole bunch of other tones, which are all separated from the input tone by an integral multiple of omega s.